So we had ended last week talking about criticisms of null hypothesis testing and whether or not this is a reasonable procedure to be even basing a science on. We had talked about criticisms based on both methodological, conceptual grounds. Okay, conceptual grounds, we have a discrepancy between what the scientific question of interest is versus what null hypothesis testing gives us. What we'd like to know is, based on these data, what's the probability that the null hypothesis is true? That would be nice, and in a perfect world we would get that, but what we actually get with null hypothesis testing is, given that the null hypothesis is true, what's the probability of these data? We do a little flip-flop in our logic, and that little flip-flop, this little adjustment from an absolute to a probability statement, kind of makes the whole thing fall apart in terms of strong logic and strong inference. Okay? And again, Cohen refers to this as the illusion of attaining probability, right? So despite what we would like null hypothesis testing to do, this isn't actually what it does, right? It's not useless, but the flip around starts to make us far less confident than it would if we were working in terms of absolutes. We also talked about non-equivalent probabilities. So we, with null hypothesis testing, get the probability of obtaining an observed data at this level or more extreme, assuming that the null hypothesis is true. What we'd like to do is get a probability that the null hypothesis is true based on the observed data. We can't just flip these two things around. We went through an example with schizophrenia, looking at, while even though we may find a case from a null hypothesis perspective, probability of a normal case, assuming, or probability of a positive test assuming a normal case is very, very low. But actually what we'd like to do is make a determinant of the probability of a normal, I got switched around here. So we've got looking at the probability of a positive test given a normal case, right? Probability of the data given a normal case. We'd actually like to know is the probability of a normal case given a positive diagnosis, and that is actually quite common, right? We're sort of turning this on its head, and even though the null hypothesis test suggests that this should be a very rare event, the actual event that we're probably interested in looking at is quite common. Okay, we had then, and that's where we had left off. So these are conceptual kind of procedural limitations of null hypothesis testing. Another criticism is that the null hypothesis is always false. We went through this, right? Did we cover this slide? We did? Okay. This idea that some population value is exactly zero, or there's that exactly zero difference between groups, is as methodically impossible, right? There's always going to be some infinitely small, and usually not infinitely small, some degree of difference between two populations. So to ask, are these two exactly the same, is problematic, right? It's a nonsensical question. And we talked about Mealy's Krebs factor, given that everything is related to everything, right? In some indirect way, if we have enough people in our sample, we're always going to fail to reject, or we're always going to reject the null hypothesis, right? And so you can start to see this in your own research when I have a p-value of 0.08, right? And so I say, well, there's no effect there. Well, if you were to double your sample size, you probably would detect an effect, right? And so it starts to become questionable if our entire statistical procedure is based on, do I have enough people to detect the difference that I know there is? Sort of starts to make this whole procedure start to fall apart. Other problem here is the reliance on dichotomous decisions. Now, to some extent, we need to have some sort of decision. We need to have some sort of criteria where we say, all right, this is a go, this is a no-go, right? Well, what happens in statistics classes and in applied analyses, oftentimes what happens is people sort of just hang back in that dichotomous decision making and start to make unwarranted inferences about studies and things along those lines, right? We talked about two different studies of intervention. One that found a significant, they were able to reject the null hypothesis. The other was not able to reject the null hypothesis, and so standard interpretation would be maybe that results are inconclusive. Sometimes we find an effect, sometimes we don't, right? But if we actually look what's going on, both of these have very small samples, right? If we look at the confidence intervals for these, there's a huge degree of overlap. This one, the second study, contains a zero estimate for the difference in their data, but it's just at the end, right? And we know that not all values in our confidence interval are equally likely. We're just right there at the cut point, right? So we've got one study that found an effect, and we say, woohoo, we have evidence that this works. Second one doesn't, and we say, well, I guess there's no effect there. In actual fact, if we're looking at this carefully, I would argue that there's sort of convergent evidence that there is probably something going on with this intervention, right? But if we're just making yes/no decisions, we don't get that far. We're not making sophisticated and critical evaluations of some of the stuff that's going on. All right, that's where we left off. Another criticism, general bias against the null, okay? We tend to associate our predictions with rejection of the null, and for good reason. If you start predicting the null in your hypothesis, you're gonna have problems, okay? Why is that? What's the problem with hypothesizing the null? What does the null hypothesis tell us? Formally. Candace?
The null, sorry, chewing.
Excuse me, a failure to reject the null hypothesis. What do we conclude when we fail to reject the null hypothesis?
That the null is true.
Okay, and that's different. I'm glad you said it, but don't ever interpret it that way, okay? So if we fail to reject the null hypothesis, are we saying that the null hypothesis is true?
No, we're really, well, yeah, that's not what I would typically say. I would say that we just don't have enough evidence to,
There you go.
you know, say that there is a difference.
Right. So when we fail to reject the null hypothesis, all we can say is that we don't have enough evidence to say, yeah, it looks like there is difference, right? We're stuck in that agnostic. Maybe there is a difference, maybe there's not. I don't know, right? And so when you're hypothesizing the null, you're saying there's going to be no difference between these two groups, you're kind of stacking the cards in your favor, right? Because maybe what I do is I just grab a sample of 10 and don't find a difference. I'm like, well, looks at that, like looks like my theory is correct. We're moving forward, right? There are some interesting ways to go through and start to test zero or near null effects, right? If we say that I'm not going to say that there is no difference. I'm not going to say these two groups are exactly the same. But if these groups don't differ more than 2 points on this test, then that difference that they have or any difference that they have doesn't make sort of have much practical impact. And if we get reasonably large samples and can try and zone in on saying that yes, it looks like the difference between these two groups is no more than about 2 points, then we can start to make stronger claims about near null effects and things along those lines. But in our standard hypothesis testing, this is problematic, okay? But what happens, because we have this bias against the null, is that oftentimes there are studies, there are dissertations, there are theses being conducted out there in the universe that are consistently finding no effects, and these go unreported. These are the sort of lost studies that no one knows about because our criteria for publication is that we do have an effect. And so we don't have an effect. All that stuff, we could have 50 studies that are trying to test out the same exact procedure. None of those hit, but then we get one study that does, right? And then what happens to that one study? We publish it, right? And so probably what happens is that one study is actually sort of atypical of what people have been finding, but now we publish it and we say, okay, we've found an effect here, and what happens is that ends up being a misleading study, right? Because it's taken out of context of all the other studies that have never found anything. Big hubbubaloo last year, a couple years ago, about sort of finding that we couldn't replicate major studies in psychology, right? And people were up in arms about it. If you understand how this all works, you're like, yeah, of course. Of course you can't do this, right? Because what happens is you get one study, not to say people are cheating or falsifying data, but in the distribution of tests, right, sometimes you're gonna get stuck at the tail. And when you get that, then you publish it, and then people say, oh, this is the effect. No, it's not the effect. The effect is way over here, right? But what happens is we have concerns about inflation of mean effects in the literature, positive bias on this, probably, and in some cases, likely grossly overestimate the true population effect, right? Other things that we have going on here is, so we often feel compelled to control for multiple tests. And this is a good thing, it's not necessarily a bad thing, but if you think about increasing the stringency of your test, arguments that this also contributes to inflation of our estimates of effect in the population, because not only do I have to find an effect, now I'm gonna crank the whole thing down with, in Bonferroni correct, for 15 different tests, right? So only those tests that are abnormally large and showing differences that are far larger than what we would expect in the typical population are those that are being reported, right? And so what happens is that those studies that do end up to be on the high end of the spectrum in terms of the difference that they found or the relationship they found, those are the ones that are studied, or those are the ones that are published, and then we read through the literature and say, okay, there's 2 studies that have found this, and this is the size of the effect, and so I'm gonna power my study to this effect. Probably you're shooting yourself in the foot, because that's probably an overestimate of the actual population effect. Just some effect sizes end up with substantial positive bias in their estimation. Furthermore, there's the irony that the sophisticates who use procedures to adjust their alpha error for multiple tests are adjusting for a non-existent alpha error, thus reducing their power, and if lucky enough to get a significant result, only end up in grossly overestimating the population effect. Why is Cohen saying non-existent alpha error from a theoretical standpoint? What's his criticism against Bonferroni testing things and post hoc alpha corrections? What type of error is he talking about? Frank, do you have an idea? Type 1, right? And why does he say people are adjusting for non-existent alpha error?
I think it's basically saying that it's the way we misinterpret p-values.
Partially. Why can I not, from a theoretical standpoint, why can I not commit a type 1 error?
That goes back to what we were saying before about null hypothesis testing, where it's saying that, there's always a variance.
Exactly, right? From a theoretical standpoint, it's impossible for me to make a type 1 error, because a type 1 error says I'm claiming there's a difference when there's not, or I'm claiming a relation with there's not, or when there's not. Well, from a theoretical standpoint, there's always a difference. There's always a relation to some extent. So the only thing that I can do is conclude a direction or a difference or a relation that's in the opposite direction of what it actually is, right? And so what Cohen is saying is, by having this inordinate focus on this type 1 error, when theoretically there's no such thing as a type 1 error, what we do by cranking up our post hoc tests and increasing our threshold is lowering our power, right? Because we're reducing the likelihood that we'll be able to reject the null hypotheses. And as a consequence of those effects that we do see that do cross the threshold for rejecting the null hypotheses are probably far larger estimates of the true population effect than what the actual effect is. And so what happens is we end up drawing erroneous conclusions about all this. People see kind of the problem of what's going on with this. What are your questions, Julie?
I'm not sure. I'll try to formulate
Yeah.
it. I feel like I'm having trouble like, with the conceptualization.
Yeah, no, and so what part did you get caught up, because other people did as well?
So I don't know if I can put it in words, but I'll try. So it says, adjusting for the non-existent alpha error, because there's always a difference in everything.
Right.
But we do that.
We do that.
So we are all grossly overestimating?
Probably systematically as a science, right? And so this is where, so we've got a conflict between, from the theoretical standpoint, what we're doing, and then sort of the practical limitations that we have in science, right? Look, we have to have some cut point, right? When, and I see this all the time, right? So you publish a paper or submit a paper or something like that, and we ran, say, maybe sort of a bunch of tests. It was exploratory or something like that. We ran maybe in the total paper, total like 15 analyses. And you get a reviewer say, you need bar and front and correct for all those. One, no I don't, because that's not an appropriate use of that correction. And two, what Cohen would be saying is that if we did only those, if this is the distribution, right? If I run a study, right, and this is my effect size, right? And this is the and this is the true effect in the population, okay? And I run individual studies to test that, assuming that I've got a good study. Just by random chance, I'm going to get studies that fall out here and studies that fall out here. Now, if I've got if this is actually a small effect, let's say 0.25, something that even falls below the threshold. This is about I'm looking at about a quarter of a standard deviation difference between these two groups, right? And this is a real difference, right? These groups, one group is about a quarter of a standard deviation above the other group, but it's a very small effect, right? But it's real, and if I have a large enough sample, I can detect it, right? But if I don't have a large enough sample, and I'm getting effect sizes that are falling around the true population effect, and I don't have a very large sample, what am I likely to do in terms of my hypothesis test? Probably going to fail to reject, right? Because I don't have enough power there to detect that small effect. But maybe, let's say, through no fault of my own, I run it and I get an effect size of D equals 0.8, right? That's a large effect, and I'm probably going to be able to detect that even with a small sample. So probably what happens then is I go through and I say, yes, this effect is here. I report this and I publish this paper, and my point estimate of the true population effect is 0.8, right? Now, it's actually not. The true population effect is 0.25, but my paper is the only one out there that was able to detect it, and it was just because it would happen to be an inordinately large difference between these. And so now, all these ones didn't get published because we didn't reject the null hypothesis. Now we've got one study out there that happened to find it. And again, I want to emphasize, this isn't because you've done anything wrong. You just kind of hit the jackpot, right? But now our estimate of the population effect in the literature is 0.8, when in actual fact it's much, much lower than that, right? And so now we have a bunch of graduate students powering their study to detect an effect of 0.8, and that's just not going to happen, because actually probably what's going to happen when they run their study, they're going to be back around here, right? And so the problem with alpha corrections, if used inappropriately and without thinking about what you're doing, is that all of a sudden, even if we find things that are a little bit farther out here, or maybe I have enough power that my effective, say 0.30, did just meet 0.05 or something like that, but then I bonferroni correct the hell out of everything, and so now that's no longer a significant effect. I can't talk about that, and the only thing that I'm getting able to report with confidence is this stuff going on way the hell on the tail, right? And so what happens is that gets published, and then we say, oh, this is the true effect, and then everybody's sad and confused when we can't replicate it, right? And so what Cohen is saying is when we go through and we use these procedures indiscriminately without thinking about what's going on, we're not doing anybody any favors. Because what we're doing is we're taking that alpha equal 0.05, and now we've made it alpha equals 0.0008, right? And the only things that we're gonna find as statistically reliable is the weirdo stuff that's hanging out in the fringes that is probably not a reasonable or accurate estimate of what's going on with the actual population. Does that help clarify some of this? Questions about this? Yeah.
Can you talk a little bit more about adjusting alpha error?
We'll get to that. So the idea is that if I run 5 tests, okay, and I set my alpha at 0.05, right? What happens is the more tests I run, the more and more likely it is that I'm going to detect an effect when there probably isn't an effect to detect. So across 0.5 times 5, across that those 5 tests, the likelihood of me incorrectly or mistakenly rejecting the null hypotheses when I probably shouldn't ends up being about 0.25, right? Sort of the same reason, this is why we don't just run a correlational, I got a big data set, and I just run a correlation matrix to see which variable is related to which variable, and I've got 40 elements in that correlation table, and I see one significant correlation, I'm like, that's it, that's the one. Now, those are the measures I'm gonna use, right? Problematic because, again, across 40, if you're testing the statistical significance of those at 0.05 across 40, it's almost a certainty that one of those will just come up as statistically significant by accident. So what we do, if we're running a lot of tests, we say, well, want to be conservative, right? And we're going to scale back, and so what we start to do is reducing our alpha level to adjust for the increased likelihood of mistakenly rejecting the null hypotheses because we've just run a number of tests. But like everything, there's no free lunch, pros and cons, right? And so this is why it's important to understand what's going on with these tests, how they work together, both from a sort of how to calculate stuff out, but conceptually what's going on to put together a strategy that makes sense given your study, the literature, characteristics of your data, things along those lines. People feeling okay about this? Okay. And we'll talk about this more when we get into confidence intervals around effect sizes and looking at, so this is the point estimate of, my point estimate of the effect in the population, but this is just one of an infinite number of estimates, and so what we want to do, just like we're looking at confidence intervals around means, we can calculate confidence intervals around effect sizes, which generally will make you sad, but it starts to demonstrate the sort of very, very low precision that we have around our point estimates of effect, and then using that information to inform sort of our assumptions about what's going on in terms of data and different psychological processes. Okay. Last thing, and we get a lot of this in some of those this consensus statement I had you read, failure to recognize the limitations of null hypothesis testing. People think this does stuff that it doesn't. Things that it doesn't do, tell us the degree which the null hypothesis is true, right? Doesn't do that. We're assuming it's true, and assuming the null hypothesis is true, what's the probability that I would obtain data of this extreme or more extreme, right? It's a different question than what we'd like it to be. Doesn't give us an estimate of the magnitude of effect, right? Well, this person, so I've got a p less than 0.001, and that means I've gotten a large effect. Like, no, it might mean you have a large effect, but it also might mean you have scads of people in your sample, and any trivially small effect is going to come up as reliable. This is a big one. Does not indicate the probability of replication, right? People will look and say, oh, well, and so they report on this study of 70 academic psychologists, found 60% believe p equal 0.1 indicated the result would be replicated 99% of the time. Nope, that's not what it does, right? We'll read a paper next semester that talks about p-values and sort of how we can take and relate that to replication, but it's not an exact statement of the likelihood of replication in a study. Okay? Direct support for the Provost theory. we see that our null hypothesis is rejected for a lot of reasons. Sometimes we got method stuff, sometimes we have measurement stuff. Sometimes there's an alternate explanation for why our data turned out the way that we did that wasn't what we had considered, right? And so this is why I think about alternative explanations about what's going on with data, conceptually what could be going on, what else could account for the effects that we've seen. Just because you rejected the null hypothesis doesn't mean necessarily that you've found conclusive support for your data. Right? All this is saying is that these data are unlikely to have occurred if the difference in the population is exactly 0. Things that our null hypothesis testing does provide, again, the probability of obtaining the results as or more extreme than those observed in the data, assuming that the null hypothesis is true. This is all that our null hypothesis tells us, right? And it's not nothing, but it's often not what we would wish it to be. And again, I've had you guys read a number of different papers that are talking about this. ASA consensus statement, Cohen's talking about this stuff. That extensive meal paper I had you read, talking about some of these things. So just trying to get this ingrained into your mind. Okay? So appropriate conclusions for null hypothesis testing. If we reject the null hypotheses, we can say that A is likely greater than B, or A is likely greater than B, or A and B are likely positively, negatively related, right? That's a reasonable conclusion for rejecting the null hypotheses, right? A is probably bigger than B, right? And we've got, this is, these data are consistent with the statistically reliable effect of A group. The population from which group A was drawn is likely larger than the population from which group B was drawn. If we fail to reject the null hypotheses, probably what we should be looking at is the direction of the actual difference between, or the relation between A and B is uncertain. How is this different than sort of our standard interpretations or our maybe undergrad interpretations of our fail to reject? What do you think, Sean?
Well, we're told that the null hypothesis has, we've seen before that significance means that there's a difference, or that failure to reject means that there's no difference. When you read the articles and see stuff, that's not what the case.
Right. And you'll see here what we've done is we've taken some Cohen's stuff and tweaked this a little bit, right? Again, if you look at this, we're not saying there's a 0 difference. We're still saying that there's a difference. It's just the direction of the relation or the direction of that difference. We don't know. A could be bigger than B, B could be bigger than A. Whatever it does, even if we calculate an effect, we might say, looks like there's a small effect. It could be this way, it could be the other way. We really don't know. We don't have enough data available to us to make a strong conclusion on whether or not A is bigger than B, B is bigger than A, or A and B have a positive negative relationship. Again, still this idea of we don't know, we don't have enough data to say, but taking the possibility that the true difference between these two groups is absolutely 0, kind of we're taking that out of the question. Questions on this? All right. So why do we have it? Like, why do we continue to have, why are we continuing to do this even though people since the 20s have been saying, hey, we've got some serious problems with this procedure? One, it's communication, right? It's a convenient way to communicate what we've got going on. P-value, we can create, we can get a calculated probability value for, I believe, almost all of our inferential statistics. All you need is a standard error to calculate a p-value, right? And so what is nice is it translates across a variety of statistics. And one of the things that becomes difficult in effect sizes is we have different effect sizes for different types of tests, right? Your effect size for a means-based comparison for a t-test is going to be different than your effect size for an ANOVA, which is going to be different than an effect size for a regression. And it starts to get really difficult to keep track of all of our effect sizes and what they all mean and things along those lines. P-values are nice, right? P-value less than 0.05 means the same thing, no matter if we're doing regressions, hierarchical linear modeling, so it doesn't matter, right? And so it's nice, it's easy, and it's convenient. It also gives us a standard cut point for our dichotomous decision-making. At the end of the day, we're more comfortable saying, yep, there is something, or no, there isn't something, right? In actual fact, hopefully as you guys are picking up, that there are varying shades of gray, right? And on which side of this statistical cut point may be more about our methods and how we've gone about measuring things than what's actually going out there in the real world, right? But in terms of, okay, this is our agreed upon standard, our p-value gives us an opportunity to say, all right, this in general is what we're gonna be able to call evidence, and no one can, and in general, people aren't gonna mess with you if you claim statistical significance if you're beyond this point, okay? Which is fine, and I'll grant that that's probably a useful thing to have, so that we don't have anarchy and chaos in science. But what I would hope for you all is to be able to understand the types of things that influence those decisions, and be able to, even if you don't meet criteria, to be able to determine, be able to guess why you probably didn't, whether or not there's nothing there, or whether or not maybe we just don't have enough people in our sample, or maybe I had to just get a really rough measurement of whatever variables I'm looking at. Probably a lot of error there. If I could look at this more precisely, I would be more likely to reject the null hypothesis. Okay, and to date, absence of a better alternative. You'll have people who do Bayesian statistics, right? And the Bayesian procedures start to get map on more closely to the types of questions that we'd actually like to know. Problem is to produce some of these Bayesian statistics, we need a lot more information than what we actually have. We can make some estimates and guesses, but it's just, again, problematic in its own way. Now, Bayesian people will probably pick a fight with me on this, and that's fine. To learn and understand down the road, but this is standard practice for psychological science. I'm going to teach you standard practice for psychological science. I'm just hoping to get you to a point where you understand what's going on and can sort of make critical evaluations on what your data say and probably what it doesn't say. Okay. Questions on this? Okay. Suggestions for null hypothesis testing? Cohen's saying we've got an array of techniques that we can use to study our theories. We have to use these sensibly. We have to be informed on how we do it, right? You don't want your surgeon to be like, yeah, no, I sort of read a handbook, a spreadsheet on how to go through and do this, and so if I just cut this way and that way, in theory, we should be good, right? Again, I think a lot of times we've got people running with scissors out there. If you're gonna use a tool, you better know how to use it appropriately and responsibly, and that's why we're spending hours on assignments. How will running a statistical test claim a difference be statistically significant, be less than 0.05, no longer sufficient, okay? In addition to hypothesis testing, we need to tell our readers something about the difference itself, confidence limits on that difference, and the power of our test. Okay? Recommendations, report your test statistics, degrees of freedom, exact p-values. P-value of 0.051, 0.150 aren't identical in terms of their fail to reject, right? I don't want to see p less than 0.05 on here. I mean, there's a couple instances where we will, because we won't have an exact probability estimate, but give the exact value, right, to 3 decimal places. And if it's lower than 3 decimal places, then you can say p less than 0.01. But in general, we're looking to get exact p-values here. Report, for the love of God, your descriptive statistics, okay? Correlation covariance tables as we get to into regression analyses. These are the fundamental. I can go through and recreate your analyses to a great degree if you give me the means and standard deviations. There's no reason, unless you're trying to be sneaky or hide something from me, that you shouldn't be giving means and standard deviations, all right? You will run into this for your thesis, for your dissertation, when you're trying to determine sort of power analyses, right, to see how many people I need to make this study worthwhile, but your source articles haven't reported means and standard deviations. We can do some mathematical algebraic jujitsu to try and work backwards to get to that stuff. Hopefully that's one of the things you pick up within this class, but it would just be nicer if they just gave it to you, right? So always provide means and standard deviations. Augment null hypothesis test with effect size and confidence intervals. Doing something new this semester. We're gonna start out with a interpretation of our effect sizes and our confidence intervals. And once you've given me that, then you can tell me about the statistical test. But by the time you've done the first two parts, there's really nothing else to report after the null when you get to the null hypothesis test, aside from, yeah, we achieved statistical significance, or no, we didn't, right? So gonna, with your assignments, focus on placing the focus of the interpretation on the confidence intervals, on the effect sizes, and then after we've got that out of the way, we can say, and also, and this isn't news because you saw it from the hypothesis or from the confidence interval, but this is the p-value. Right? Reporting methods and software using the calculation of statistical tests, effect size, and confidence intervals. This is a good thing to do, but SAS isn't doing t-tests better than SPSS, isn't doing better t-tests than R. A lot of the stuff we're doing isn't going to make a big difference. But if you start to get into some more nuanced, different types of contrasts and things like that, then some of that stuff becomes important, right? And the big thing that comes into play here is your effect size. And tell people how you calculated your effect size. There are 1,000 different ways, not 1,000, but there's a lot of different ways to calculate an effect size depending on how you're thinking about these data, right? And so if I just say that you calculated an effect size, and this is the effect size, what's going to happen is I'm not going to trust you, and I'm going to calculate my own effect size, and I'm going to see a discrepancy there. Now, maybe it's because we're calculating it different, or maybe you don't know what you're doing, or maybe I don't know what I'm doing. I don't know, but I don't know what's going on. But if you say, this is how I calculated the effect size is based on pooled standard, pooled variance estimates across groups, then I know exactly how you did it. And then I can have a discussion on whether or not I think that's a good way to do it or a bad way to do it, but at least I know how you did it, right? Lots of different ways, as we'll see, to calculate these effects. Make sure that you're telling people how you went ahead and did it. Report the results of all relevant hypothesis tests. This gets into some of the p-hacking stuff. Ends up being a bigger issue, not a bigger issue, but you experimental people in the field, bigger sort of emphasis on. I was talking with Sean this afternoon about for experimental people, they make you do like 7 actual studies before you can actually publish anything. And now he's like running meta-analyses on the 7 studies that he did. Like, it's a pretty high bar. But what you want to not do is go through and run 1,000 different tests and then not report all the tests that you didn't run, and only report the tests that turned out to be statistically significant, because that's starting to misrepresent the likelihood that probably some of those just came up as just because of random stuff. Okay, and then and I'm going to hit you hard on this. Be accurate and precise in your interpretations, right? Don't say fail to reject the null hypothesis, so we conclude there's no differences between these two things, right? Don't do that, right? It's easy to do it, and this is our common language. I went through through the t-test slide, revised sort of the interpretation that I provided, and it took me a long time, right? Because I was trying to use language that's not typical of how we usually talk about statistics, but hopefully we'll get some practice in here. We'll get you ingrained in so that you can start to use your terms precisely. With these types of analyses, if you change your language a little bit, it changes what that means, right? And so if you think I'm being cruel and nitpicky, maybe, but it's because I love you all and I want you to do so well. That was weird. That came out weird. Right? It is on camera. Well, so down the road from the bank, Clap's been creepy for years. Exhibit B, but it was some weird stuff that was going on. But so be precise in your language. This is Tess and I going through and providing feedback on your stuff. Go through, look at that stuff, and make changes to the way you're interpreting things, because if you don't, it'll start to aggravate me. But hopefully you'll go on from that. Okay. And then some stuff on reporting p-values. So, questions about any of this stuff up to this point? So hopefully you're all jaded and at this point and have come to the conclusion that our entire science is based on a sham. It's a house of false cards, and we know nothing. Not necessarily true, but some very, very real limitations to our null hypothesis test. And so we have to play by the rules of the game, right? But just knowing how these pieces and parts fit together will help you evaluate your own research and the research of others much more critically. Cool. All right. So, t-tests. It's been 4 weeks until we actually get into tests that people use actually in the universe, okay? T-tests, to this point, what we've done with our hypothesis testing is comparing a sample mean to a population, a reference population with a known mean and standard deviation in theory, right? So we've used a lot of examples like IQ scores and SAT scores and things along those lines. If I have a group and I'm wanting to compare it to some known reference value, some value where I know the population mean, I know the population standard deviation, what I'm looking at is our single sample z-test. Again, example, here we have a rat population with a known population mean, or known, the mean weight in the population is known. The mean variance in the population is known because we've bred these animals to be very specific in their characteristics. And what we want to do is we want to give them the sample stuff, and then we want to see, has this caused a change in sort of the weight or things along those lines, right? In this case, we know the mean, we know the population, we know the variance of the population. We're looking at a single sample z-test. Problem is that our single sample z-test generally requires more information than we have available to us. We generally don't know. We need to know the population variance in order to calculate the standard error of the mean, but in most settings, we don't know the variance, right? If I want to, say, look at sort of the effects of some experimental manipulation on on the reaction time to some behavioral task. Maybe I know what the population mean is, but probably not, right? We probably don't have good data on across the entire population of interest what the variability is on that growing performance on that task. And so we can't then do a sample, a Z, because we don't have enough information. But we've got kind of a solution here. Because we know that the sample variance is an unbiased estimator of the population variance. So the idea is what we can then do is use our sample variance as an estimate of the population variance, and then use our sample variance to estimate our standard error so that we can go about and conduct our test, right? So in the z-test, we have a population variance, but in our, if we don't have access to that, our data, we can calculate a variance estimate for our data, because our variance estimate that we've calculated is an unbiased estimator of the population variance. Maybe we can just use that sample variance and substitute that in for the population variance, and then calculate our standard error from there, okay? And recall that a sample statistic is unbiased, and you'll hear about this, talking about statistics being unbiased, efficient, and things along those lines. These are good things to understand because it'll give you better insight into what people are talking about. But recall that a sample statistic is unbiased if the average value of that statistic across replications is going to be equal to the population parameter, okay? So same thing about the mean, right? The mean is an unbiased estimate of the population mean, because across an infinite number of replications of a given sample size, the mean of the sampling distribution is going to be equal to the population mean, right? So people are comfortable with unbiasedness and what's going on. So if I do this enough and I replicate this over and over again, does the average of the variances that I collect, will they equal the population variance? The answer is yes, because variance is an unbiased estimate. And if you remember, how we get this unbiased estimate is we go through and we start changing the denominator of our sample variance, just by a little bit, right? So, again, recall we had this discussion about our sample is never gonna capture the full variance in the population, right? It's gonna get a restricted range and probably stuff that's coming out of the middle. We're gonna miss the tails, right? And so what we do then, when we're calculating the sample variance as opposed to the population variance, we take our sum of squares, which is the sum of the squared deviations, and we divide by n minus 1, right? We're making the denominator in the calculation of our variance slightly smaller, right? And it's going to make our sample variance slightly larger to make up for the underestimation if we're just calculating population variance. Okay. Remember this, remembering why we do this and why this makes sense. And so again, if I have a very small sample hijum, what's my correction going to be in my in the calculation of my sample variance? It's going to make it big, right? If I have a very small sample, I'm going to get a big adjustment in my sample variance relative to the population variance, right? Because I've just collected maybe 5 guys out of the middle. I've strongly underestimated my variance, and so I'm going to have a pretty big increase. Rachel, what if I have a very large sample?
You're gonna have smaller variance.
Well, a smaller correction to that variance, right? Because I've got a big sample. Presumably, my larger sample is going to be more representative. I'm going to do a better job of catching people out on the edge, and so it's still going to adjust it a little bit, but to a much larger or to a much smaller degree than if I have small samples. Okay. So people sort of remembering why we make this adjustment to our calculation of our sample variance in order to make it an unbiased estimator. Okay. So we're feeling good, we're feeling happy, right? We're like, sweet, but we've got a problem, okay? Although our sample variance as an estimator of the population variance is unbiased, what happens is we start to get problems when we look at the sampling distribution of our variance, okay? When we look at the sampling distribution of our variance, what happens is the distribution of our sample variance, okay? Same concept as the distribution of sample means. But when we look at the distribution of sample variance, what happens is our sampling distribution is skewed, okay? So again, if we're talking about the sampling distribution of our variance, the distribution of the variance estimates from all possible random samples of a particular size that could be drawn from the population. So same thing as distribution of sample means, we're just looking at the distribution of variances now, right? And what happens is we plot this out, we don't see the nice normal shape that we get with means, we get this skewed distribution, okay? Any thoughts on why we get a skewed distribution as opposed to a nice normal distribution? Yeah.
I would think because the samples will be less likely to have greater variance because the scores will be clustered around the mean. So the sample variance, you're going to get a larger, more scores towards the,
Towards the tail?
Yes.
Yeah.
Yeah.
And that's part of it, right? Is sort of as this increases, we can get larger and larger and larger estimates of variance. What's our bound on the low end? 0, right? Now, if we're looking at distribution of sample means, I can have means that are very, very high above the sample of the population parameter, and I can have sample means that are very, very low in the right. And so I get this nice distribution, right? I can have equal likelihood of getting stuff that are very, very high versus very, very small. With variance always has to be positive, right? And we can't have negative variance. And so what happens is we see things shift up towards the low end of the scale and then tail out. Conceivably, from a theoretical standpoint, we could have variance equals sort of approaching infinity, right? And so we're going to get this tail that goes out. This becomes more problematic when we have a small sample, right? When we're looking at the sampling distribution of variances for a small sample. So what's the distribution of all possible, what's the distribution of variance estimates from all possible samples of 10 that could be drawn from a population, that's very small. I can get massive variances, right, that are way out there, but everything is gonna be stacked up because I can't have anything less than 0. And so what happens, because we don't get our distribution of, our sampling distribution of our variance isn't normal, what happens is that on average, in a randomly selected value of our sample variances is likely to underestimate the population variance. Okay, so what's going on here? How can our sample variance be unbiased, but if we randomly select a variance estimate from a given study, it's likely to underestimate the population in terms of our sampling distribution? So this line here is the mean, right? And that represents the true population. And so this is the mean of the sampling distribution, so it's unbiased, right? So here we would say, so this is a distribution of sample variances with N of 5 from population. Mean has a mean of 5, sample variance is 50. This line at 50 is the true population variance, right? And it's the average value for this distribution of sampling means. So why would I expect that any random value from the sampling distribution that I would select, why would I expect that to be an underestimated population variance? What do you think, Judy?
So I think when you pull a random sample, and you again, like Candace was saying, they're most likely gonna be around the mean.
Mm-hmm.
So most of them it's not gonna have that high of variance, and so that's why you have like more of your random samples will have lesser.
Yeah, okay.
And then the real population obviously has.
Okay. What happens to our sample? What happens to the mean in a skewed distribution? Yeah.
I mean, it's for the direction of the mode.
Not the mode.
One of these, yeah.
Recall that in a distribution like this, the mean of this distribution is going to get pulled out to the tail, right? Because we've got outliers, we've got scores way out in the tail that are being calculated into the mean, right? And so even though those scores are very, very unlikely, they're still having an undue influence on our mean. So the mean of our sampling distribution variance is getting drug out towards the tail, right? And so if I calculate the mean of my sampling distribution of the variance, my mean is equal to the population variance. The mean of this distribution is variance of 50, right? But what happens is that mean is getting pulled out towards the tail, right? And so if I say, okay, here's my distribution here, right? And so here's my mean, right? So my mean is this value, but if I randomly draw a value from that distribution, is it likely to fall at the mean? No, it's likely to fall up here, right? The only reason that my distribution of sampling variances is unbiased is because I've got these large values that are dragging that mean out, right? And it balances it out, right? So our sample variance is unbiased, right? The mean of my distribution of sampling variance is going to be equal to the mean of my going to be equal to the true population variance, but that's only because I've got very large values dragging this out. If I randomly select a value from this distribution, it's probably going to be one of these, right? But these are not here, they're an underestimate, right? And so thinking about this carefully, down the road, sort of exposure now will start to help you think about sort of other biases and statistics and things like that. Distribution of sample means is fine, right? Everything's nice, everything's normal, everything kind of lines up here in the center. When we look at the sampling distribution of variances, we got a skewed distribution. And even though our test statistic is unbiased, because the mean of the sampling distribution is equal to the population value. If I randomly select a value out of this distribution, it's probably gonna be on the low end. It's gonna systematically underestimate my population variance, right? So by adjusting my denominator, I kind of fixed things, right? I made my sampling statistic, I made my statistic unbiased, but then when I look at the distribution, the sampling distribution of that statistic, now I'm back to underestimating the population parameter, because even though across an infinite number of samples of a given size, the average of those variances will equal to population variance, but if I, in my individual study, it's still gonna be an underestimate. People kind of get what's going on with this. It's tricky, and I had to, sort of, every time I go through, I have to sort of reorient myself to this. But questions on sort of why this is problematic, because it's important for understanding why we're using T statistics as opposed to just running everything with a Z. Okay, so what happens is, on average, any randomly selected value of our sample variance from this the distribution of sampling distribution is likely to be an underestimate of the true population, right? So here's the population value, but the majority of my values are falling over to the left of it. That's probably where they're going to come from. So I'm going to systematically underestimate my variance. If I'm systematically underestimating my population variance, what's going to happen is I'm going to get an inflation in my test statistic. Why is this, Gabby? If I'm underestimating population variance, why am I going to have test statistics that are too large? Remember that any test statistic that I have is going to be any test statistic that I calculate is probably going to be some ratio over a standard error, right? My standard error is calculated as my variance over my sample size, right? And if this is too small, what's going to happen is this is going to be small. My standard error is going to be too small. If my standard error is too small, it's going to make my test statistic, when I plug that into the denominator, I'm going to take a value and be dividing that value by a systematically smaller value. And what's going to happen is I'm going to get my z-tests are going to be too large. I'm going to say that this sample is unlikely, or the probability that I'm saying that, oh, this is an unlikely thing to happen, is it's going to be too large, right? Because if I have systematic bias in my variance, and if I go through and I change that from the population value to my sample variance, now all of a sudden what's happening is that this value is smaller than that value, and so this is going to be smaller. I'm going to put a smaller standard error, and what's going to happen is this is going to be too big, right? And so now all of a sudden, this statistic that I'm calculating is not Z, it's something else, and that statistic doesn't follow my Z distribution that I know and love. Okay. People understand kind of how this, and again, this is why I'm harping on you guys, like, sort of look at these ratios and think what happens. Like, a lot of this stuff is just what happens if I divide something by a smaller or larger number, what happens with my outcome. It's a lot of this stuff boils down to that. So what happens, and this is a problem, is that if we try and use our Z formula and sort of use hypothesizing with Z, but we're using sample variances instead of our known population variance, what happens is we systematically overestimate our test statistic. Our test statistics are too large, and we're going to be rejecting the null hypotheses more often than we should be, okay? And the degree to which we're overestimating or our test statistics are inflated are a direct function of our sample size, right? If our sample size is very low, we're more likely to sort of grossly underestimate the variance. If we grossly underestimated the variance, then our standard errors are going to be far too small. Standard errors are far too small, our test statistics are going to be way too big, and now we're in a pickle. Questions about this? So, the solution, people working in breweries. William Seeley Gossett, AKA student, sharp-looking dude with some sweet glasses and a mustache here, chemist for Guinness, okay? And what they're trying to do is they're trying to run some stuff with calculation of sort of recipes and looking at yeasts and things like that. And he's saying, well, I don't have population values for these things. And what's happening is I'm getting a systematic overestimation of what I should be getting, and my statistics are all off, and we need to do something about this. And so what Gossett did was, in addition to other people, but he's the one who gets credit for formulating the T distribution. He published papers under the surname Student, and so we end up with what is now known as Student's T. Student's T specifies the sampling distribution of the T statistic, which uses our sample variance as an estimate of our population estimate. Okay, so if Z So if our Z that we know and love is our mean value divided by, or minus the population mean, or the standard error of the mean, and standard error of the mean is the square root of population variance over our sample size, right? This is our Z test, our single sample Z. T then is our mean minus our reference value over our standard error. And our standard error is the square root of our sample variance over N. So this is a subtle difference, right? This, though, has a known value. So the distribution of this Z statistic is known. It's our beautiful bell curve that we all know and love. But as soon as we start calculating, when we switch over and we start substituting our sample variance for the population variance, what we start to get is a different family of distributions. That distribution starts to change. It no longer is a Z distribution. It starts to, the shape of that distribution starts to become a little bit different. And because the shape of that distribution is a little bit different, our probability values corresponding to different test statistics get a little bit different, right? Our T distribution actually represents a family of curves, each with a different shape depending on your degrees of freedom, okay? Degrees of freedom are determined by the number of people that you have in your sample, okay? What happens is our T distribution approaches a normal curve as our degrees of freedom approach infinity. So, what we've done with the Z distribution, that's actually just the distribution of all possible Z scores that we could get based on samples with a known population mean and variance, right? Here, with the T, all of a sudden we have to substitute our sample variance in there. We know a random sample or variance estimate is probably going to underestimate the population variance in terms of our sampling distribution. And so what happens, and we know that because that underestimation is going to be a direct function of our sample size, what happens with, and this is what Gossett worked out, is what is the exact distribution of these test statistics if we're substituting our sample variance for our population, or our substituting sample variance for the population variance, okay? And so what we get is our T distribution specifies a sampling distribution of our T statistic for a given degree of freedom. Our T, as I wrote up here, is same thing as with our Z, right? We're just calculating our standard error using our, here we've got sample standard deviation over the square root of N. You can do the square of the variance over N2, same thing. But what happens is our critical values start to become more and more extreme as our degrees of freedom decrease. Right? If our degrees of freedom decrease, what does that mean? What does that imply about our sample size, Zach? Right. So as our degrees of freedom decrease, that means our sample's getting lower. And if our sample's getting smaller, what does that imply about the estimate of our estimate of the population variance? Trent?
More accurate.
More inaccurate in which direction? Smaller. And if our variance estimate is smaller, what does that do to our our test statistic? Makes it larger, right? And so as our degrees of freedom, our t-distribution start to be based on a smaller and smaller sample, what happens is our benchmarks for what we can claim statistical significance starts to go out farther and farther, right? So what happens is as our sample size decreases, we have a greater and greater threshold for what we will talk about as a statistically significant effect, okay? What happens with this is a systematic correction for the inflation of our test statistic when we compute our test statistic with our sample variance as opposed to a known population variance. Okay, so Steph, of these curves right here, which color is associated with the lowest degrees of freedom? Right, okay. We see as our t-test is a family of curves, and as our t's get smaller, they become more peaked with these flat tails, okay? As our sample size increases, as we get closer and closer to a z distribution, our family of t curves starts to approximate z as our sample size go larger and larger, okay? To the point when we're working with samples of 200-300 people functionally, and you'll see this in your tables. Functionally, we're working with a standardized curve. But again, the whole purpose of our t statistics was to work with small sample stuff. And if we're working in small samples, we're going to systematically underestimate the population variance. And if our sample variance is an underestimate of the population variance, we're going to get an inflation of our test statistic. And so we want to go through and actually plot out what the distribution of my test statistic is for a particular degree of freedom, and then what I can do is then start calculating probabilities under that curve. Okay. Someone give me an interpretation of this number here. Gabby, how do I interpret standard error? What is this value telling me from a conceptual standpoint? What do I interpret standard error to be? Anybody help her out? Important to know, the answer is always standard error. Okay. Remember, there's a number of different ways we can interpret this, right? We can talk about the standard error as the expected error in the estimation of our sample, right? We can talk about it as the expected difference between replication, randomly selected replications, right? We can talk about it as the expected distance of my sample mean from the true population mean, right? Go back through and read through that standard error slide again. A lot of different ways, but again, if we take a look at what we're doing with this test statistic, we're saying, all right, here's the difference that I observed. Here's the difference between the mean that I got and my population reference value. This is the discrepancy that I've got. We're going to take that over the top of how much of a discrepancy I would expect just based on my sample size and my variance, right? So if I were to do this again and again and again and again and again, if there really is no difference, how much should I expect that estimate to jump around? And if I've got a small sample size, Candace, do I expect that estimate to jump around a lot or a little?
Which estimate?
If I'm estimating the mean, if I have a small sample size, am I expecting large deviations between randomly selected samples or small deviations? Large, right? And so if I've got a small sample, my standard error is going to be a lot higher, right? And that's saying I've got to get more of an observed difference before I can claim, yeah, there's probably something going on. Than if I have a very large sample, giving me a very precise estimate with a very small standard error. And then if I'm getting anything that's jumping beyond sort of a very close deviation, I'm gonna be more confident that what I've got is actually detecting an actual effect versus just some random fluctuations, okay? Again, always remember with this, numerator, this is your signal, denominator, this is your noise, right? How much static would I expect just based on just random replications of this? And if what I see is a lot more than what I would expect just based on random jumping around, then we're more likely to reject the null hypothesis. So again, standard error, talk about this in the difference between population parameter and sample statistic, right? That's measurement error. But the difference between the population statistic and any randomly selected replication, the difference between any two replications, or sort of the amount of difference that I would expect across replications in the sampling distribution. So another thing that's interesting, if we're thinking about back to earlier lectures, our family of T curves, particularly our T curves with very low degrees of freedom, right? Very small samples. Classic example of a leptokurtic distribution. Leptokurtic, are we talking about positive kurtosis or negative kurtosis? Hijong, you remember? Positive, right? Leptokurtic is positive kurtosis. We get peaks and very thick tails out to the side versus negative kurtosis. What do we get, Hijong? What does that distribution look like? Anybody remember? You're about to. This is neither here nor there, but this is an actual page and figure out of students' original publication. Apparently, in sort of the earlier 20th century, not uncommon to provide a little illustration in your paper. Here, student says, in case any of my readers may be unfamiliar with the term kurtosis, we may define mesocurtic as having blah blah platycurtic in the normal curve of error, and leptokurtic longer tails. I myself bear in mind the meaning of the words by Maria Technica, where the first figure represents the platypus, the second kangaroo, noted for lepping, although perhaps with equal reason they should be hares! Exclamation point, right? So platykurtic, sort of boxy, round like this. Leptokurtic, sort of very tall, peaked, with thick tails on the end. Courtesy of student 1927. I've been trying to put in my own illustrations in my reviewers say that is not necessary. Go ahead and take that out. T distributions, okay? If you go back through and you look at your tables, we'll see all of these have been wonderfully tabled for you effectively as compared to your Z table, right? Here what we're doing in order to read this, down the left column you have your degrees of freedom. Degrees of freedom for our single sample t-test are going to be your sample size minus 1, although that will change depending on what test we're looking at. Here you have level of significance for a one-tail test. Probably not going to worry about that too much. Here, your level of significance for your two-tailed test. So what we would do is we would say, let's say I have a very small sample of 5 individuals. What I would do is say, all right, for my independent sample t-test, that gives me 4 degrees of freedom. And so I would find 4 degrees of freedom here, and then find my alpha level here. So if I'm running a test at 0.05 with 4 degrees of freedom, my critical value here to identify 0.025 in the positive and the negative tail for the two-tailed test, my critical value is 2.776. Rachel, do you remember what our critical value is for 0.05 in our Z test, or in our Z table?
For 0.05,
Mm-hmm.
1.96.
1.96, okay? So if we're running this in a Z test, our critical value, our threshold, our benchmark for claiming statistical significance would be a Z statistic that exceeds 1.96. Here, if I've got a sample of 5 individuals, My critical value is 2.776. I've got to get a lot larger difference relative to my standard error in order to claim statistical significance with my t-test than I would with the z-test, right? And so what's happening here is we're getting a systematic adjustment for the underestimation of the population parameter because what we have with these with the t-distribution is a known distribution of test statistics for a given sample size. And so if we were looking at this from here's my distribution of scores when I have a sample of 50, right? And here's a sample of scores that I have when I have 10, right? And so what we know, because this is a known distribution of test statistics, what I can do is then start saying, all right, what's the probability of a score being at or more extreme than this for a sample size of this given size, okay? So your t-distribution is actually a family of curves, and the shape of that specific curve depends on your degrees of freedom. Questions about this? Questions about how to find your critical values in your t-table? T-table isn't going to give you an exact p-value. Z-table does. It gives you probability values. T-distribution doesn't, because you would have an entire z-table for every single possible degrees of freedom. That would be a massive tome. And so with your your t-table, it just it gives you different alpha levels. So what's sort of 50% the up half, this, and so we just go through and find our critical value here. So, putting it all together. Z-test, structure to determine whether a random sample mean likely to have occurred in a population with a known mean standard deviation, or excuse me, mean variance. We reject the null hypotheses. We interpret this as evidence that scores were unlikely to have been drawn from a population of a given mean and standard deviation. Okay? With our single sample t-test, what we're doing is we're using this to compare sample mean to a known reference mean, right, when the population variance is unknown. Okay, here we're looking at the t-distribution corresponding degrees of freedom to account for underestimation of the population variance, given our sampling distribution of our sample variances here. This bias becomes increasingly large as our samples become increasingly small. Threshold of significance becomes greater for smaller versus larger n. And again, as our degrees of freedom increase, we get to a point where basically our t-distribution is basically a z-distribution with enough people, right? But as we start to get smaller and smaller, providing a correction for our smaller or our underestimation of population variance, critical values for single sample t and our t-table. Okay. Questions to this point? People feeling comfortable? So we're basically doing the same thing we did with the z. I just want you to understand why we can't just use z-distribution or z-tests to go through and test stuff where we are substituting the sample variance for the population variance in our statistics. Questions? Cool. All right. Factors influencing our t-test. Difference between our mean and our reference value, right? What happens, Hijong, when the discrepancy between my observed data and my reference, when my reference parameter gets bigger? What happens when I see a larger discrepancy? What does that do to my t-test? What's that? Right, it's going to get bigger, right? The larger difference that I see relative to my reference value, everything else held constant, it's going to make my test statistic larger. We also see sample variance. What happens, Rachel, as my sample variance gets smaller?
Sampling error is going to get smaller.
Mm-hmm. My standard error is going to get smaller, and what's that going to do to my test statistic? things, all other things held constant.
I'm going through examples in my head.
Oh, no,
Yeah, 'cause
just
the-
don't go through examples in your head, just look at the equation. What happens when my sampling area gets smaller? What happens in my test statistic?
So,
My T value here.
it's gonna be larger.
It's gonna be larger, right? So as my sample variance gets smaller, it's gonna make my standard error go down, which is gonna make my t-test larger, right? And then sample size. As my sample size increases, it's gonna, I'm assuming a more precise estimate, everything else held the same. This is dramatically gonna reduce my sampling error, or my standard error, and if my standard error is smaller, it's gonna make my t-test go up. So again, one of these things, when we're looking at sort of violation of assumptions of our tests, oftentimes what happens is that the consequences for our violations end up screwing around with our standard error, right? And if our standard error is messed up, that screws up our test statistics, our null hypothesis testing. Oftentimes, what happens is we'll violate an assumption, doesn't do anything to the point estimate remains fine, but it starts screwing around with our standard error. And because all our standard error is the entire basis of our hypothesis testing structure, if we start being uncertain about our standard error, we have biased standard errors that starts to impact our inference. All right, quick word on degrees of freedom. Okay, degrees of freedom are confusing to people. They're always confusing. They're confusing to me even, but sort of basic, not that I'm not easily confused by things, I'm often confused about most things, but degrees of freedom, from a statistical standpoint, we're talking about the number of values in the calculation of a statistic that are free to vary around. Okay. So for example, let's say that this is a true statement. X plus Y plus Z is 24. Stephanie, what does X equal?
I don't know.
Yeah, why not?
Because there's three different parts of the equation.
Right? Could it be -4?
Anything.
Exactly, it could be anything, right? X is free to vary, like it could be an infinite, like it could be any real number, maybe even unreal numbers. I don't know, it could be an imaginary number. I'm not a math guy necessarily, but X is free to vary, all right? But let's say that we say that X is 5. Trent, what's the value for Y? Still don't know. Still could be anything, right? But as soon as I say X is 5 and Y is 5, now all of a sudden, what's Z? Now Z has to be 14, right? So in this equation, we have 2 degrees of freedom. We have 2 cases where our values can be anything we can imagine, right? But as soon as one's locked down, and then the other's locked down, we've run out of degrees of freedom. Once we have 2 set values, that final value is no longer a variable, it's a constant. We know what it is, right? And so from a statistical standpoint, we would say that this equation here has 2 degrees of freedom. In the case of our single sample t-test, our degrees of freedom is n-1, okay? The reason how we get to this degree of freedom, we lose a degree of freedom when we're calculating the sample mean, or when we use the sample mean to calculate our variance estimate, okay? So, because our variance is a function of the deviation of each score from the mean, right? When we're going through and calculating our sum of squares is calculated as sort of every single score subtracted from the mean of the scores, right? But because the sum of x plus m has to equal 0, the final x value in that distribution is fixed. It's not free to vary, right? It can't be whatever it is, right? So we say, here's the mean, right? As we go through, those x values could be anything at all, right? Hopefully they're not. Hopefully they're reasonably reasonable values, but they could technically be anything. By the time we get to that last deviation score, however, that x value has to be some specific value in order for everything to sum to 0, because only one, and so that's where we lose our degree of freedom. With the single sample test, because we're only using one variance estimate, we end up with a degree of freedom of n-1. Okay. So this ends up being kind of abstract and not hugely relevant unless you're getting into the sort of the theory and the proofs of statistics, but it's important to know degrees of freedom, what degrees of freedom are associated with certain types of tests, so that one, you can calculate things effectively and then catch when other people are trying to pull shenanigans on you. All right, quick word on p-values. Again, we've been hitting this over and over and over again. I'm hoping that the repetition will drive this deep into your brain. P-value, probability under a specified statistical model that some statistical summary in the data will be equal to or more extreme than the observed value, right? And when we're talking about a statistical summary here, we're talking about a test statistic, a mean, something along those lines. Again, looking at this as being how incompatible these data are with a specified statistical model. You got the things that a p-value does not indicate. Again, review of what we just went through. But this is something that you will be presented with, is how I calculate my p-value. Okay. What we do with a p-value, and so this is the difference between the one-tailed and the two-tailed test. Our z-tests, right? We had our distribution, right? And we said, well, we're going to calculate the probability of here is my test statistic. Let's say it's 3. Okay? What's the probability here that I found? And let's say it's 0, 0, 1. Okay, something along those lines, right? For calculating the p-value for your test statistic, what we would do is calculate that value here, and then we would double that, get 0.002. Because what we're looking at with a two-tailed test is what's the probability of obtaining observed data that's plus or minus a z-value of 3, right? So not only do we have to account what's going on here, we have to account for what's going on here at this negative value. So with our hypothesis testing, we're accounting for both tails of the test. For our t statistic, let's say that for my t-test, I want to conduct a 0.0, I won't say alpha to 0.05 for a two-tailed test. What I need to do, and this is what is being tabled in the books, is figure out what proportion of that specific t-distribution for that degrees of freedom, let's say the degrees of freedom equals 20, right? For that distribution with degrees of freedom equal 20, how much, what's the value here where this is 2.5% is in that tail and 2.5% is in that tail, okay? And that's what determines our critical threshold. So for whatever that value is, that's what's being tabled in that t-table there. Okay. So, and if we want to get in, if you're interested in sort of the difference between one-tailed and two-tailed tests and kind of what we're doing, pros and cons, things along those lines, Howell recommends in general using two-tailed tests. You know, in certain cases where you may have a very specific a priori hypothesis about the direction of a test, we could calculate a one-tailed test. And in a one-tailed test, what happens is we would put all 5% into a single tail, and so what would probably happen is then we would get a smaller t-statistic here, right? Because we're not worried about anything going on down there. We're just worried about what's going on here. But in psychological research, sometimes the things that we think should make people better make people worse. And sometimes we think that should get an increased outcome actually creates a decreased outcome. If I put all my eggs in one basket and I get something way on the other side, technically I can't look at that, can't talk about that because this was the area in which I was testing, right? And so in general, we would use two-tailed tests based on sort of recommendation from Howell. And that's oftentimes in the literature, if you start using one-tailed tests, it raises red flags that you were just kind of trying to arbitrarily reduce your criterion for rejecting the null hypothesis. Here you see p-value calculator. These online tools are fantastic. I would encourage you to use this. So if we go to stop listening to me, Cortana. So you see p-value calculator graph, this GraphPad website. This is phenomenal. I use this all the time. It's fantastic. Let's say, so I need a p-value for, I've got a 3.12 with 34 degrees of freedom. Compute my p-value, 0.0037. Really slick, really easy. You can't get p-values directly from our tables unless you have an exact statistic that falls exactly on a specific degree of freedom. So go through, take a look at that, and take things from there. Okay. Where are we at in terms of time? Oh boy, I'm taking over. Let's stop, take a break. Have I? Yeah, it's about 4. Stop, let's take a break, and we'll come back and jump into this next example. All right. So I want to go through one of these first sort of hand problems here. Harkening back to controversy over age of library books. Hot topic. All right. So you guys know the old song and dance, old librarian, new librarian. Fist fights over how old the books are. But here in this, what's that?
Classic movies.
Right? Yeah. It's sort of a cliche at this point, really. But whatever, we'll go with it. So again, new version comes. Old librarian says 20 years old. Student says this guy doesn't know what he's talking about. I'm going to show him up. And randomly selects 30 books and records a public date for each. Sample has an average of 23.8 years. Sample variance is 67.5. Okay. First thing, in a sentence, state the null hypothesis being tested. Candace, what's the null hypothesis being tested in a sort of sentence?
1 second, I'm rereading it.
Okay.
The null hypothesis, you said?
Yeah.
Okay, so it would be that the books in the library are 20 years old.
Okay.
Or, yeah.
Good, good, and probably in this case that would work. The one thing I would want you guys to encourage you guys to be focusing on is sort of that recognizing the population or the null or your hypotheses are talking about population parameters, right? So you might say something like the average age of the population of books in this library is equal to 20 years or something like that, right? If we're talking about this library, I kind of assume that that's part of the population, but in general, right? Framing your hypotheses in terms of population parameters. If we were to state these using symbols, we might write that our null hypothesis is that books equals 20, right? Alternatively, alternate hypothesis, population of books not equal to 20, right? We're saying maybe they're younger, maybe they're older, we don't know, it's just not 20. So, first thing we need to do here for our calculations, calculate a 95% confidence interval for the point estimates of books in this sample. What do we do first? Rachel, what do we need before we can start calculating confidence intervals?
We need the standard error.
Perfect. I told you standard error was always the right answer. Standard error in this case, right? We're going to take square root of the variance here, 67.5. We've got 30 books in the sample. This gives us a value of 2.25 for our standard error. Then I wanna, calculate my 95% confidence interval. Gonna take my point estimate, my mean, which is 23.8. Plus or minus. Now it gets tricky. What do I need here? What do you think, Sean?
You need your, T interval, that's what you're using for the confidence.
Oh, lovely. And why do I need a T instead of a Z?
Because it is, you're estimating the approximation of many different, whole sample needs rather than just one specific one.
Right, right. So because we don't know what the true population variance is, we're estimating the population variance based on our sample statistics. We've transitioned from a Z to a T, and so for our critical value, we need to be using our T statistics in the calculation of our confidence intervals, as opposed to our standard 1.96, 2.58, 3.29 Z values, right? And so, Jeff, I saw you had it up there. What did you get in terms of our critical value for a 95% confidence interval with how many degrees of freedom here?
That's like 29.
29. And what did you get for your for the Z or the T?
2.045.
Something different. You're probably right and I'm probably wrong. Let me see. Oh, 29. Yeah. You're right. It's 2.045. Okay, yep. 2.045. I had 19 degrees of freedom instead of the appropriate 29, even though we have 30 books. But do people see how we got degrees of freedom? Take the number degrees of freedom for this, n minus 1. We've got 30 people in our sample, so we're looking at 29 degrees of freedom. Okay. So we've got our point estimate, our critical value here, and then multiply this by our standard error, which we just calculated as 2.25.
Does that need to be, square rooted,
What's that?
the 2.25,
Does this need to be taken the square root of?
to make it 1.5? I don't know, I thought it did.
Did I calculate that wrong?
I don't know.
Maybe it's
Maybe
possible.
I did.
No, I get the.
I think.
So you got 67.5, 30, divide that. Oh, good job, yes. Look at that, I tried to come prepared and I screwed the whole thing up. Thank you. You will.
And one more question, so where did you look to get the T value?
Okay. Trent, share with people where you got to. You got 2 people who've already showed me up today. I'm gonna be sad and sulk
So
right now.
just, the appendix of the book, on page 702, is 29 degrees of freedom, and then the significance for 2 delta test of 0.05.
So you got where we got that? Okay, cool. Other people clear? This is fantastic. You know what I'm gonna do right now? I'm gonna pretend that I did this all on purpose to make sure that you're paying attention. The fact that both of you caught me is absolutely fantastic. I am very excited about all that. Okay, so we've got our confidence interval, and then what we will do is take this, someone work this out. Tell me what we get for our lower bound here, because my values are wrong. Zach, what are you getting? So one, how much?
21.237.
21.23 and, oh, is that, okay, that would be our lower bound, what's the upper bound? Judah, what do you got?
Yeah, so the standard error is 1.5. And so, it's cool.
No, this has been a complete disaster, back to front.
That's why I was making that weird
Yeah,
face.
but-
I was like,
There we go. 1.5, there
Yeah,
we go.
but then, yeah, I got the lower bound being, 20.732, and the upper bound 26.868.
Okay,
Um,
so we got 20.73. Okay.
Yeah.
I'm glad all this is on camera. 20.73.
You might be out of frame, so sure.
No,
And-
no, I made sure I get the.
And 26.87.
26.87. Okay, there we go. Despite my best efforts to confuse you, you've gone through and figured this all out. So, okay, we've made it through. We've corrected the error in our standard error. We've gotten the right critical value. We've gotten the right standard error there, and we now have an appropriate interval estimate of a lower bound of 20.73, upper bound of 26.87. Does someone want to give me an interpretation of that confidence interval? No? What do you think? Rachel, I'm gonna pick on you again. Tell me, give me an estimate of that interval.
So, you had an infinite number of random samples.
Okay, I'm gonna stop you there. Let's not do that.
Okay.
Yeah, that's like confusing, you're on the right track, and you would give me a perfectly acceptable answer. But it's, anytime we start in a paper talking about infinite number of random samples, we're gonna lose 90% of our people. So, but from a conceptual standpoint, how would we interpret that interval? And we had a number of different options. Anybody help her out?
Given the available data, a 95% confidence interval suggests it's reasonable to conclude that the mean age of books in the library is between 20.73 and 26.87 years.
Yeah. Right. Again, remember that our confidence interval is just, it's just our point estimate, if you said to say, tell me exactly what the average age of books in this library are, tell me what the population parameter is, we would say, well, I guess I'll tell you 23.8. And then if you said, is that the right answer? I'd say probably not, right? Because we know we've estimated that with some error, right? This is our best guess, but based on the data that we've collected, we would say any value between 20.7 and 26.8 would be consistent with the data that we've gathered here, right? And so we can talk about these as a range of plausible values, right? Based on these data, lower bound estimate, a reasonable lower bound estimate of the population mean would be 20.7, reasonable upper bound 26.8. We can talk about what's our margin of error is 2.445. 2.07. Right, so our margin of error is about 3.07. So we could say we would expect no more than our sort of the point estimate of our of the population to mean to be within plus or minus about 3 years, right? So we would expect no more error in our estimation of about 3 years. Again, as you're working through and I'm having you incorporate and interpret confidence intervals, go back through, take a look at the slide from sort of 2 lectures ago, and think about how can I talk about this in a way that makes sense, and so play around with different explanations. Tess and I will help you and say, yeah, this looks good, or maybe tweak it a little bit like this. You could say over an infinite number of replications, we would expect 95% of the intervals calculated from an infinite number of replications of sample size 30 to capture the, but then what we end up with is that we don't know where this interval falls. Maybe it's one of the 95% that we would expect to capture it, but maybe it's not. And so we're sort of stuck with a mathematical statistical explanation when what we're looking for is some conceptual explanation for what our data are saying, right? So based on these data, based on the available data, we would expect that estimates of the population age of books falling anywhere from about 20.7 to 26.9 years is about reasonable, right? So if I were to estimate the mean age of books to be 26, that's reasonable based on the interval estimate that we've got here, right? We could also say that values of the population age of books in the population, or the mean age of books in the population in this library, falling between 20.7 and 26.7 years would be consistent with these data. Values falling outside that range would be relatively implausible or inconsistent with the data that we've captured here, right? Again, the data that we've captured is kind of qualified, right? So this interval, this is our estimate, but it's based on sort of our assumption that these data are reasonable and representative. People comfortable with the confidence interval piece here? Okay. And then the last thing we're doing now, after we've gone through, we've calculated our confidence interval, and we already know, are we going to reject the null hypothesis here? What do you think, Hee-jung? Or based on this confidence interval, are we going to reject the null hypothesis at alpha 0.05?
We cannot use it.
It's close. It's close. What value are we looking as to whether or not it falls within that interval estimate? With the 1/10, with the single sample t. So we're looking to see if 20 falls in there, right? And so our lower bound is 20.7, right? And so before we even conduct our t-test, we know that we're going to reject the null hypothesis, right? And so this is why people will say everything that you get outside of an exact p-value, you already get with your interval estimate, right? But we'll go through and do it because the man makes us conduct hypothesis tests, right? And so our t statistic here is going to be 23.8 minus our reference value of 20.0. This is what we've observed. This is the discrepancy that we've observed. The error that we would expect based on just random selection of a sample is about a 1.5 point difference. And this is going to give us a t statistic of, so we got that for me? Okay, and because 2.53 exceeds our critical value of 2.045, we know that we've rejected the null hypothesis, right? If we were to map this out, and we're saying that, what's our critical value over there? Someone? 2.045, and our test statistic is 2.5, what? 2.53? Okay, right? We've got it out there, it's in the tail, and so we would reject the null hypothesis at p less than 0.05, right? Now, because we want specific p-values, what we then might want to do is go and pull up our calculator to get a specific, and so our value is 2.53 with 29 degrees of freedom, and our p-value would be 0.071. Or no, not 071. 0171. And so technically, if we wanted to make a technical interpretation of that probability value, we would say that given a sample of 30 people, the probability of obtaining sample data of this value or more extreme is expected only 1.7% of the time, assuming that the null hypothesis is true. So assuming that the true population age of books is 20 years old, only about 1.7% of the time would we randomly select a sample of 30 books where our mean age would be a difference of 3.8 plus or minus, right? Because we've got a two-tailed test here. People kind of see that procedure and comfortable with that. Again, not terribly different than what we're doing in our z-tests. It's just kind of taking that and playing around with different critical values because we're working with small sample stuff instead of values with a known population mean and standard deviation. Any questions before we move on? All right. Effect size, right? We've been talking a lot about effect size. Effect size is an estimate of the absolute magnitude and effect in a population, independent of sample size, right? So our hypothesis testing is all based on sample size. As your sample size goes up, our standard error goes down, and if I get a big enough sample size, anything's going to be statistically significant, right? But just because something's statistically significant doesn't tell me how much of a difference there is, right? We often want to say, oh, that's p less than 0.001, that's got to be a big effect. Not necessarily, right? If I've got, say, 1,000 people in my sample, I can find correlations of, 0.1 or less that are probably going to come up as statistically significant just because I have so much people in my data. All my hypothesis test is saying is this reliably different than zero? An actual, like an orthogonal relationship. There is zero relationship between X and Y in the data. Well, just because it's statistically reliable and reliably not zero doesn't mean telling me anything about how big that effect is, right? Now our effect size, on the other hand, is an estimate outside of disregarding the size of our sample. What is our point estimate of the actual effect in the population? Like any other statistic, we're looking at our effect size is giving us an estimate of some population value out there in the universe. What's the magnitude of the relation between X and Y, or how much of a difference is there between group A and group B? But as we've talked about before, and one of the reasons that people I think have problems with effect sizes is we get different metrics of effect depending on what analyses we're using, right? So the analyses that are the effect size that we're going to be calculating for the comparison of two groups is going to be different than the metric of effect if we're looking at regression analyses or ANOVA and things along those lines. So I've got to keep a lot of things, a lot of different metrics in my head all at the same time. And also the calculation of even things like D, as we can see, varies depending on how I want to conceptualize my effect. And so, unlike p-value, where the calculation is identical no matter what you're doing, effect sizes start to get a lot more variation. It's a lot more information to keep in your head. Not everything is going to be the same across all things, and so people sort of get uncomfortable with this and don't want to do it, right? or we'll start reporting Ds for everything in the universe. Now, R is kind of a universal metric, and we can convert from Ds to Rs and things along those lines, and we can move back and forth. But in general, for practical purposes, you should be reporting effect sizes that correspond to the test that you're actually doing. Okay? And what we can do is use these effect sizes to help augment our interpretation. To give us more meaning, not only is our A and B reliably different, or is there a difference between group A and group B? What's the magnitude of that difference? How much of a difference are we talking about? That's often more interesting than are they different at all, right? So effect sizes for a single sample t-test, this is pretty simple. There's only so many effect sizes you could calculate for a single sample t. We can calculate a raw difference as a simple measure of effect. This is just your mean value that you observed minus your reference value. Okay? Now, this is a very simple measure of effect size, but it can be incredibly meaningful, right? Let's say that the average salary for a university professor is sort of X number of dollars, right? But we see that, and we know this to be true across all universities across the nation, but we see people, say, in California, university professors' salaries seem to be higher, right? And we could run, we could sample the university professors' salaries, run a single sample t-test against the mean value of the population, and see if these salaries in California are reliably different than the overall population, right? But what we could also do is we could just calculate the difference between the average salaries that we've got in California from the population mean, and say it's $20,000. That's just a raw difference, but $20,000 means something to us, right? We know what $20,000 is, right? And so you could calculate a standard effect size, but you could also just say that university professors in the state of California make, on average, $20,000 more than the national average. And that's meaningful, right? So if you're working with units that mean something, things like weight, years of life, right? Money, distance traveled, things along those lines, just a raw difference can be kind of a meaningful effect. But sometimes that actual raw difference isn't meaningful, right? I'm giving you an arbitrary personality scale where your score, if I say, oh, someone got a score of 15 on this personality measure, probably doesn't mean anything to anybody, right? It's completely arbitrary units. In this case, some sort of standardized effect starts to become useful, because what we're doing is we're starting to sort of talk about the discrepancy that we've seen in units of standard deviation, right? And if we are thinking about things in terms of normal distributions, if I say someone scored 3 standard deviations above the expected value, what does that tell you? Gabby?
They scored a lot higher.
A lot higher. 3 standard deviations is a lot, right? If I say they scored a quarter of a standard deviation above, you say, okay, well, fine, but that's not a great deal, right? And so what we've got here, we start to calculate at a very simple level for our single sample t is Cohen's d, right? And we're talking about, we're operationalizing the magnitude of our effect in units of standard deviation. Not unlike our z-scores that we've done before, right? Anytime you see a d, you should be thinking some sort of deviation in terms of units of standard deviation. Calculation of d for a single sample test is easy, right? You guys got your mean value minus your reference value over some estimate of your standard deviation. In a single sample t, how many estimates of standard deviation do you have? Just one, right? Just whatever I've collected I have no other standard deviations to use. I'm stuck with this one standard deviation. I have 0 options in terms of selecting which standard deviation I want to use, right? and so very easy to calculate our D here. You can also calculate your an approximation of Cohen's D based on your T statistic, right? You can take your test statistic, divide that by the square root of n, and that should give you an approximation for D. You see little asterisks here? This is because I don't want you calculating this, because you are also calculating the D. Just go ahead and calculate it here, right? This is for if someone's reported a t-test, but they haven't given me means and standard deviations, and I have no idea what their effect size is. I can take their t-statistic, if they've given me that, take that divided by the square root of their sample size, and now I've got an approximation of D here, okay? But you all will have all the raw materials to be calculating D based on sort of the mean and standard deviations, so do that. That way, Tess and I don't have to try and figure out why your effect size estimate is way different than everybody else's. It should be way different, but it'll be different enough to notice, okay? Interpretive standards, these are benchmarks. Small effect, that should not be D equals 0.2, that should be D equal 0.3. Tess, can you shoot me an email and remind me to fix this? Okay. So a small effect is going to be, no, scratch that. Nope, it's right. It's right. Tess, don't email me. Sorry about that. Yeah, so small effect, a D of 0.2, okay? What we're saying is the deviation from our reference value is a difference of 2/10 of a standard deviation, or 1/5 if you prefer. That seems weird. 2/10 of a standard deviation. We've got a 2/10 of a standard deviation increase or decrease relative to our population parameter. Cohen, in an excellent book, talks about a standard or an effect size of 0.2 being about the difference in height between 15 and 16-year-old girls. Okay. Small effect, there's a difference. There's a statistically reliable difference, but it's probably not something we're going to be able to detect sort of just by eye, right? There's a real effect there, but it's small. If you lined up 15 and 16-year-old girls, I might not be able to sort of say, oh, this group is systematically taller than that group. A medium effect, about a half standard deviation, a D.5. Cohen identifies it or describes this as the difference in height between 14 and 18-year-old girls. This is a visible effect, right? This is something that I can see. If I lined up a bunch of 14-year-old girls and 18-year-old girls, I could say these young women are taller on average than this group of women here. Large effect, 0.8 of a standard deviation. Cohen identifies this as a difference in height between 13 and 18-year-old girls. Okay. And so just to clarify, so Cohen didn't create an entire effect size system based on the heights of adolescent girls. Just sort of a visual example that people could say, okay, I can kind of see what that would probably look like in terms of, this is very clear, very large, very obvious. This is observable. This is something that probably falls below sort of just basic scrutiny, but something that's there in terms of our statistical estimates. Okay, so these are our interpretive standards. These are Cohen's benchmarks to say, okay, if you painted me into a corner and said what's small, medium, large, this is kind of what we would be talking about. But again, sort of the weight that we attach to this starts to become dependent on what we're studying and what we're taking a look at, right? And Cohen says in his text, he's like, do not use these indiscriminately. This isn't a substitute for rejecting, failing to reject them on hypotheses where we're saying that a small effect is always this and this and that. It's just general interpretive benchmarks to try and give us an idea for the things that are going on, right? We may have studies where we find a small effect, but that small effect is very, very important, right? If we're looking at, classic example is, aspirin study, right? All of a sudden we see a small effect, a reduction in maybe fatal heart attacks by 2% in the experimental group, but whoops, okay, we're not fooling around. That's very, very tiny. We probably wouldn't even detected that effect if we didn't even have massive groups of people, but it's small and it's reliable and it's enough to shut down the studies because of ethical concerns and things like that. Versus, I don't know, if I find a difference in reaction time of 2/10 of a standard deviation and it's a half millisecond, maybe that has application. So just taking a look, calculating your effect size, recognizing that this is interpreted in units of standard deviation relative to the reference, your reference mean, and then making interpretations accordingly. So effect size for our single sample test is pretty easy. We don't have that many options here. We only have one estimate of standard deviation. Standard deviation, our standardizer, as we start to get to multiple two sample tests and things like that, this starts to get a little bit more difficult, or not difficult, but it just, you have more options. Questions about effect size? Okay, effect size is our, remember, it's our estimate of what's the relation or discrepancy of the population. Again, it's a sample statistic referring to some hypothetical effect in the population, but the nice thing about this is I can go through, maybe I failed to reject an or I failed to claim statistical significance for my test, but I've got a small sample. What I've got is something that's about a medium effect, and I can say, well, I can't say with confidence, I can't say yes, we have evidence of a reliable difference based on these data. However, sample's small, power is limited. Point estimate of my effect suggests about a half standard deviation increase in this group relative to some reference point. So I'm not ready to throw the whole thing out yet, right? We're to encourage replication, larger sample, and make more precise estimate, and it's likely that this effect will come up in future research. Questions about this? Cool. All right. Wilkinson, always provide some effect size estimate when you're reporting p-value. Always present effect size for the primary outcomes. Helps to add brief comments that place these effect sizes in practical and theoretical context. We must stress again that reporting and interpreting effect sizes in the context of previously reported effects is essential to good research. Okay, I just reviewed a paper and I need to write it up that was looking at some sort of stuff, and so they're looking at sort of, oh, what are the properties of this measure, that measure, but completely failed to put it in contact with any of the other stuff that had ever been done. And these are common measures, right? Like, I don't care about what you found. Like, how does it relate to what everybody else has found, right? I have no idea whether or not what you found is reasonable and about what other people find, or not reasonable, what other people find, right? So in thinking about making interpretations, say, okay, this is what we found for our primary effects. This is about the magnitude of effect that we detected. This is how it relates to other studies that have been out there doing things, right? To start to get something that comes with this, talk about as meta-analytic thinking, like how does my study compare to the other stuff, instead of trying to just talk about my study in isolation. You're gonna probably come up short on material if you're not taking into account other stuff. Okay. All right, another example. Let's see if I screwed this one up too. This will be fun. This is what you get trying to crank out calculations right before you come into class. All right, here we go. Again, IQs and things along those lines. Flynn effect, we've got an old test, we're having new people take it and want to see whether or not we have evidence of this Flynn effect, where scores in the population taken today are substantially larger or reliably larger than average scores when this test was normed. So in a sentence, state the null hypothesis being tested. Here, we may say something along the lines of sort of the average score on an IQ test developed in 1980 in the current population is equal to 100. Okay? So we're talking about sort of the population score among individuals today is equal to our reference value when it was originally normed in 1980, which would be 100. Right? Our alternative hypothesis, our alternate hypotheses are here. We've got mean today equals 100. Alternate mean today not 100. So Steph, what's the first thing I need to do here? If I'm going to calculate my 95% confidence interval?
You need to get your critical value.
Okay.
That's my first step.
That's your step? We could do that, but what do I wanna do first instead? What's always the answer? What do we need to get? Standard error, okay. Standard error is going to be what value? Someone give me my value that I need. What goes in the numerator of my standard error?
Variance or standard deviation.
Variance or standard deviation, all right, what's my variance or standard deviation in this problem? Candace?
Do you need to calculate that from the sum of squares?
Yeah, we do, right? So here, I've got a sum of squares, right, but I don't have a variance. And so my sum of squares is gonna be 6,000 over what? John?
16.
Is it gonna be 16? 15, there we go, right? N minus 1, right? So we've got 15 people in our sample, but I need to calculate my sample variance, not my population variance. So I have to take that sum of squares divided by N minus 1. So that's 6,000 divided by 15 gives me a sample variance of 400. Okay. So my standard error will now be the square root of 400 over 16 equals there we go. Okay, I did it right that time. Standard error of 5. Okay. So for my 95% confidence interval, is going to be my point estimate of 121 plus or minus, what's my critical value here? Trent's got his book open. Trent's doing all the heavy lifting for people in terms of 2.131. So I was scared. I was nervous to even like write it down because I thought I'd gotten it wrong again. Standard error of 5. Okay. And if we go through and calculate this out, we get 10.35, 131.66. Tess, I'm going to pick on you. Can you give me an interpretation of that confidence interval?
So, given the data, the range of plausible values for the population mean, like IQ would be about 110 to 130.
Yeah, perfect. Only thing I might change just for the content, right, or for the context is say range of plausible values for of the current population mean on this IQ test developed in 1980 would be anywhere from 110 to 131, right? So putting this within the context of the problem, so what we're trying to get at with this stuff, right? And if we talk about this, right? So we already know, we're going to reject the null hypothesis or fail to reject the null hypothesis. We're going to reject the null hypothesis. Why is that, Steph?
Well, because it falls in there.
Okay.
So 121 does fall.
It does. What happens when our point estimate doesn't fall within our confidence interval? What do we know? That we've jacked up our confidence interval, right? We've made a calculation error, right? And so, but this is important, right? Because you will see this back, oh, this is my point estimate, and then here's my confidence interval. Point estimate is over here, confidence interval is over here. There's an error to be made. What are we looking at that hasn't fallen in this that we know, how we know that we're going to reject our null hypothesis? What's our
Oh,
reference
the
value?
original score.
What's that?
The original score?
The original score, which
the
is?
original average score of 100.
Yeah, right. And so 100 doesn't even fall in our confidence interval, so we already know that we're gonna reject the null hypothesis at p less than 0.05, right? And so, what we would then do, talking about this in terms of, so based on, our available data, we would say that, we would estimate the current population average on this 1980s test to be, about 121, 95% confidence interval suggests that reasonable lower bound limit for that estimate, about 110, with an upper bound estimate of 132, okay? Which starts to give us a sense for sort of what our error is, right? And so this, we only have 15 people, I mean, so we've got about a 20-point difference. That's a lot of points on a, well, no, about a 10-point difference on an IQ scale. That's not a huge level of precision, right? But what we've got is such a large increase relative to what we would expect it to be if the norms had stayed the same, right? That we've pushed this all above. Okay. What we could then do, provide an index of the absolute magnitude of the difference in current scores relative to those in 1980. Calculate our D, right? So we've got 121 minus 100 over our, our standard deviation. What's our standard deviation here? 20, right? This is important. Be careful when you're calculating your standard deviations and your standard error. It's easy to get these things mixed around. If you divide this by your standard error, what have you got? What does that give us, Candace?
What's that?
If we take the difference between our observed data and our reference value and divide it by our standard error instead of our standard deviation, what did we calculate?
The standard error of the distribution of variance scores.
Okay. Well, that would be our standard error. Since we've calculated our t statistic, right? If we take the difference, because what we're going to do is we're going to do our t, which is 121 minus 100 over 5,
yeah.
right? If we accidentally switch around our standard deviation for our standard error, what we actually calculate was our test statistic and not our effect size, right? Or if we divide, throw in our variance instead of our standard deviation, we're gonna get an effect size that's way too small for anything like that. So as you're working through problems, it's important to make sure that you're dividing by the right thing, okay? But in this case, so if our variance is 400, our standard deviation is 20, which gives us an effect size of 1.05. Yeah.
So, we're dividing by our standard deviation of the sample.
Yep.
But
And why are we?
not of the population.
Yeah, and not the population, and why not the population?
That was my question.
Yeah. Why not? John?
You don't know.
You don't know it, right? We don't have access to the population standard deviation.
But these are norms, so we do for this one, right? For an IQ test?
We would, yeah, okay, so I see what you're getting at. Yes, that would be a good argument for why we're even doing this in the first place, right? But maybe we say, well, I'm not confident in those norms because and that would be the argument, I guess, is because we actually don't know so the population mean and standard deviation on this score among people today is unknown, right? And so normally we'd say this score would have a standard deviation of 15. Maybe it's smaller now because we knew what the population mean and standard deviation were when people were taking this in 1980. We actually don't know it now, and so we're going to use our sample variance to estimate that. Okay, but yes, no, that was good, that's a good catch. And this is the reason why we rarely, ever use z-tests for our hypothesis testing, because we rarely know the population variance, and if we don't know the population variance, we're into working on t-distributions. Good question. So, Heejun, can you give me an interpretation of this effect size of 1.05? What do we always interpret our effect sizes in terms of? Standard deviations, right? So what we might say with this is we might say that participants in the current study scored on average about a standard deviation above the expected value of sort of the population mean when the test was normed or something like that, right? So we have individuals in our sample scoring a full standard deviation above what we would expect given sort of the norming of this test in 1980. So it's technically 1 in 500ths of a standard deviation. It's fine. You're talking about it, right? We would report it as D equal 1.05. Typically, I would encourage you to report D's to 2 decimal places. And so you report that as D equals 1.05, but if you're talking about it, we could say about a standard deviation increase relative to the normative mean in 1980. And then finally, what we're going to do, conduct a hypothesis test at alpha equal 0.01, along with an interpretation of your findings. Are we going to reject the null hypothesis here? What do you think, Zach? Probably. What's our only point of hesitation if we're looking at this confidence interval versus our hypothesis test?
Well, our confidence interval is 95%.
Right.
And we're looking at 99.
Right. And so is our critical value for a 99% for a test at alpha equal 0.01, is our critical value going to be larger or smaller than if we were to conduct that test at alpha 0.05? So we're looking to conduct this test at a greater level of precision, right? At alpha 0.01 instead of alpha 0.05. So is it going to make our critical value, when we go through and look at our table, is our critical value going to be bigger or smaller?
It's gonna be bigger.
It's going to be bigger, right? Because we're less tolerant for type 1 error, right? We're going to decrease that portion of the distribution in the tail, and so we're going to set those benchmarks out a little bit farther, right? So if we go through and we calculate our t-statistic here, so we've got our deviation that we see between our observed and our expected divided by our standard error, gives us a test statistic of 4.20. That's pretty big, right? And if we go through and we were to look at our critical value in our table for alpha equal 0.01 for a two-tailed test, we should get a t-critical of 2.947. Is that what other people got? Anybody looked at it? Okay. So if you can see, so at alpha alpha equal 0.05 for our 95% confidence interval, our critical value was 2.131. If we increase our confidence to a 99, or we're testing this at alpha equal 0.01, we see that our critical value is larger, right? We've taken those states, we've moved them out, so that it's even more difficult to reject the null hypotheses. But here, our critical, or our test statistic of 4.2, that's a pretty large statistic. It easily surpasses our peers. Stephanie?
Sorry, I was writing.
Oh, no problem.
Okay.
So if our test statistic is 4.2, critical values just a little under 3, do we reject or fail to reject the null hypothesis?
You would, reject.
Reject. There we go. We would reject the null hypothesis, right? And we would claim support for a statistically reliable difference between average performance on this test that we see today relative to the expected value when this test was normed in 1980. Okay? And then what we would want to do is tie all this together into some comprehensive interpretation that takes sort of the question of interest, takes the evidence that we've got here, right, our confidence interval, our effect size, and our hypothesis together to say, yes, so we would say that there is a difference. This difference is about this much. This is about the level of precision that we have here. These would be reasonable estimates of the true population difference ranging from about 110 to about 131, somewhere in the vicinity of about a 10-point difference there. Yeah.
So if you calculated your confidence interval to correspond to the alpha, so 99 confidence interval,
Mm-hmm.
would you say that you might not reject the null because it could contain 100?
Okay.
So you're making your confidence interval larger, right?
Exactly, right? Now, based on my test statistic versus my critical value, even if I made that confidence interval larger, you're exactly right. Would it contain 100 based on the hypothesis test that we've conducted here?
No.
No, right? Because again, and this is why, when we're trying to get people to incorporate confidence intervals, they'll say, well, so I did my hypothesis test and I rejected the null hypothesis, and my confidence interval confirms that, or my confidence interval also indicates that's actually not correct, because it's all based on the same stuff, right? Your interval estimate just gives you a range of plausible values, or an upper or lower limit, or an estimate of precision of your test. And so you're absolutely right, Candice. If we were to calculate a 99% confidence interval, our interval would be larger, right? But we know, because we've gone through and run the hypothesis test, that it still would contain that point estimate of 100, because otherwise we would have failed to reject the null hypothesis here. Does that make some sense? So I mean, we can do it if we go through and we say 121 plus or minus 2.947 times 5. Okay. So if we go through and calculate that as a 99% confidence interval, our lower bound is 106.3, upper bound is 135.7. And so still doesn't contain that our point estimate of 100, right? So we've increased our confidence interval because we don't want to be 95% certain. We want to be 99% certain. So I was like, okay, well then it's somewhere between here, right?
Mm-hmm.
But for those of you who are familiar with intelligence testing, or currently in assessment right now, what if I told you that the average intelligence score is somewhere between 106 and 135? How precise is that estimate? That's huge, right? They're either a little above average or super genius, somewhere around there, right? That's pretty big, right? So that's additional information that you would know given some of the background. And so I don't expect you to know all of that necessarily for these problems, but something to think about when you're in your own content area, right? To be like, yeah, no, this is a pretty big, we're failing to reject the null hypothesis, right? So we're saying there is, it looks like there is people in today's population scores, on average, score higher on this test norm in 1980 than people did when the test was normed. On average, we're expecting about a standard deviation increase in scores relative to where things were before. However, if we're looking at that, sample small, we've got 16 people, or the precision of our estimate isn't real good. I mean, so the increase could be, our point estimate for average scores in the current population could be anywhere from 110 to 132-ish, right? So we've got a lot of variability, but we're seeing such a discrepancy here that it's very clear that pretty strong evidence that scores today are larger than they would have been in 1980. Questions? All right. Done. That's one minute. Just wait, I'm going to talk to you about assumptions. Calm down. Yeah, so we're way ahead of schedule, and so this is good. You guys are fantastic. We're moving along. As we continue to progress through some of these t-tests, we'll talk about whether or not we need to adjust stuff on the syllabus or not. So let's work on problem set 4. Getting those prepared, ready to rock and roll by Friday at noon. Okay. Go back through because in that one I'm having you make interpretations on confidence intervals and things like that. Don't worry about effect sizes. If you want to calculate effect size just to be fancy, go ahead and toss them in there. I'm not going to be upset with you. Technically, we hadn't gone through effect sizes for that problem set, so you don't have to necessarily worry about working those into your interpretation. But what I do want you to do is make sure that you're working in those interval estimates appropriately, providing some context and some meaning with that, focusing on that interval estimate and then following up with the z-test. If you have questions, come talk to Tess or I, and what we'll do is we'll start out with doing some SPSS work when we start up next Wednesday. Okay? So next Wednesday, come with all your handouts that we didn't get to. Come with your data sets, and then also, so for some examples here, we've got examples, that we'll go through in terms of write-up stuff, so you can go through and take a look at, again, not a template, not something to cut and paste, but, and you won't necessarily have a headspace for what we've done, because this is the stuff that we're going to work through in SPSS, but an idea of the types of things you might want to do as you're thinking about putting together interpretation. So, sound good? Okay, cool.